Now that we've taken some good looks at like quadratic surfaces, how to graph lines, how to graph planes, and now how to graph in more general settings, just quadratic surfaces, the next bit of kind of prerequisite material, if you will, to get to multivariable differentiation and then eventually multivariable integration is vector valued functions. We need to first have a good grasp of vector valued functions before we can step into the realm of multivariable calculus. So let's start with defining what a vector valued function is. And I'd also like to think about this kind of geometrically as we define certain things. Let's start in 2 dimensions, say x and y, okay? And we have some curve, right? Y equals f of x is some curve in the plane, right? You tell me an x value, and then the function eats the x value and it spits out the y value, right? So how do functions work, right? They eat a real number. So let's take this to be R2, right? Like, let's say we're looking over the reals here. So x eats a real number, or f eats a real number x, and then spits out f of x, which is another real number y. So the input is x and r, which is just a number. And the output, y and r, is also just a number, right? So f takes a number and spits out a number. Now, vector valued functions behave slightly differently. How a vector valued function behaves is now, here's some curve, f of x, y equals f of x. We can parameterize this curve. We've seen actually one of the first lectures of the course, we saw that we can parameterize a curve, meaning we look at this in terms of a parameter t, say. And so now for a vector valued function, which I'd like to start abbreviating by VVF to save myself some space and time, the input is going to be our parameter. However, this curve has been parameterized. So we'll say t and r, right? So this is at some t value, let's say at time t. And the output is going to be a vector now and not just some number. And what vector are we going to take? We're going to look at the vector with initial point, the origin, and terminal point, the function at time t. And so we'll say the output is a vector given by f of t, comma, g of t, because x and y are both a function in t. You remember from parametric equations, we can parameterize, when we parameterize a curve, both x and y become functions of t. And so our input is going to be where we're at along the curve in terms of this parameter t, and the output is going to be the vector from the origin to that point. And so as t, let's say, in this case, if t were getting bigger, we'd be traveling in this direction. And so as t varies, what does our function look like? Well, it's just a family of vectors. And if t were to, so these should be vectors, right? Not curved arrows. These should be linear. Okay. And so we'll represent a vector valued function by r of t. This will be a vector valued function. And so what we say is r of t equals the vector f of t comma g of t, where again, the input or the domain is our parameter, is whatever set our parameter belongs to, right? So in this case, the domain is the real numbers because I'm letting t vary from negative infinity to infinity. And the output now is a vector corresponding to f of t, g of t. So let's just see an explicit example here. And let me quickly say this extends in 3 dimensions and will work a lot in 3 dimensions. It's nice to get an intuitive picture in 2D before you step up to the 3rd dimension. But in 3D, we would have a vector valued function given by r of t equals, and then it could be like f of t, comma, g of t, comma, h of t, right? And if you will, or if you'd like it in standard unit vector form, f of t I hat plus g of t j hat plus h of t k hat. And we may see more vector valued functions expressed in this form. So let's look at an example of just what, like how can we graph a vector valued function? So first, let's consider r of t equals 4 cosine t I hat plus 3 sine t j hat. So before we can like graph this, let's understand what plotting points looks like. So let's plot the following points: r of 0, r of pi over 2, and r of 2 pi over 3. Okay, so what's r of 0? Well, when you evaluate a vector valued function at a given point, it just means you everywhere there's a t, you plug in the number that you're evaluating at, right? So we're evaluating at 0 here. So let's say this is the vector then 4 cosine of 0 I hat plus 3 sine of 0 j hat, which is the vector. Cosine of 0 is 1, so in the x component we have 4. Sine of 0 is 0. So we get the vector 4, 0. Now how about r of pi over 2? Well, r of pi over 2 is going to be 4 cosine pi over 2 I hat plus 3 sine pi over 2 j hat, which is the vector. Then cosine of pi over 2 is 0, sine of pi over 2 is 1, so that looks like that'll be the vector 0, 3. And here you can see you plug in a number and you get out a vector, which is a little different than the functions that we've observed so far. Let's calculate, maybe I can do it up here in red, just to keep it on the same screen. Let's do r of 2 pi over 3. This is 4 cosine 2 pi over 3 I hat plus 3 sine 2 pi over 3 j hat, which looks like it's going to be the vector. Cosine of 2 pi over 3 is negative 1/2. So that looks like we'll get negative 2 in the first component. And then the second component, sine of 2 pi over 3 is root 3 over 2. So it looks like we'll have 3 root 3 over 2. Okay, and so here's r of 2 pi over 3 is the vector negative 2 root 3 times 3 over 2. So here's how we plot points, and plotting points is what we'll use to graph vector valued functions. So let's see some examples of graphing vector valued functions. Okay, let's start with a 2D picture, and then we'll do a second example that's a 3D picture. So let's look at the vector valued function given by what we just looked at. 4 cosine t I hat plus 3 sine t j hat. Okay, I wasn't writing SOS here. Cosine t, there we go. And let's graph this. Graph r of t. Okay. And let's make a plot. T and R of t. So we can start to see what's going on here. And on the right, corresponding to the points we've plotted, we'll put them in the plane and then see if we can map out what this shape is going to be, or what is this vector valued function representing, right? Functions in the plane represent a curve. And let's see what kind of curve this is representing. So if we plug in t equals 0, we saw in the last example that that's the vector 4, 0. And so when t equals 0, we go to the vector 4, 0, which is 1, 2, 3, 4 units in the x direction, 0 units in the y direction. So here's our first point over here. And this is the vector 4, 0. Now, let's look at like pi over 4, say. If we go to pi over 4, well, it's going to be 4 times cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So it looks like we're going to have root 2 over 2 here. And then the next one will be 3. Sine of pi over 4 is also root 2 over 2, but now it's 3 root 2 over 2. 3 root 2 over 2. Okay, so we find the vector root 2 over 2 in the x direction is bigger than 1, right? And then 3 root 2 over 2, we're going to get something here-ish. Okay, this terminal point corresponds to the vector, and this is at the angle pi over 4, right? So it's root 2 over 2, comma, 3 root 2 over 2. And how about pi over 2? We saw pi over 2 was 0, 3. And so at the angle pi over 2, we have the vector 0, 3. And I encourage you to maybe do this for the rest of the unit circle. Like, what's 3 pi over 4? What's r of 3 pi over 4? R of 3 pi over 4 looks like it's going to be negative 2, or excuse me, negative root 2 over 2, and then 3 root 2 over 2, right? And so at the angle 3 pi over 4, we're at the vector negative root 2 over 2, 3 root 2 over 2, right? And then what about pi? Well, if we're at pi, it looks like we're going to be at the vector negative 4, 0, which is here, right? We're at angle pi. This is negative 4, 0. And I encourage you to go around the rest of the unit circle and confirm that what we get is an ellipse. Let me draw this out a little more here. So this represents an ellipse where the semi-major axis is 4 and the semi-minor axis is 3, or meaning the horizontal axis is 4 and the vertical axis is 3. And so this is one way we can understand vector valued functions. Notice in the x component, the coefficient was 4, and in the y component, the coefficient was 3. That tells us it's an ellipse with horizontal axis, or horizontal radius 4 and vertical radius 3. And so this is one way we can understand vector valued functions, by looking at their graphs, is just to plot points. And at points, these represent the tips of the vectors, and then you can connect the dots with the tips of your vectors, and you see what you get. And so let's do a 3D example. So here's 2. Let's graph r of t equals cosine t I hat plus sine t j hat plus t k hat. Okay, so again, let's graph t and r of t. And now our picture is going to be 3-dimensional. So let's look at the 3D coordinate system here. Now, if we graph 0, r of 0 looks like it's going to be cosine of 0, which is 1, sine of 0, which is 0, and 0, which is 0. So at t equals 0, we have the vector 1, 0, 0. Now let's look at pi over 4. If we look at pi over 4, well, cosine of pi over 4 is root 2 over 2. Sine is root 2 over 2. Sorry, root 2 over 2. And then t is just going to be pi over 4. Right? And so that means we're marching 1 unit in the, or sorry, root 2 over 2 units in the x direction, root 2 over 2 units in the y direction, and then up pi over 4 units. So that would put us somewhere here in the vector. Looks like this, kind of coming out diagonally out of the screen, right? This is the vector root 2 over 2, root 2 over 2, pi over 4. And let's keep going. What's pi over 2? Pi over 2, right? Because if you project here, draw a line, this angle should be pi over 4, right? Because we were at pi over 4. And this angle pi over 4 should live in the xy plane. So now pi over 2 should lie along the y-axis, right? And so if we plug in pi over 2, it looks like we'll get 0, 1, pi over 2. So we're in the y-axis. We're 0 units in the x direction, 1 unit in the y direction, but now we're up even higher. Now we're at pi over 2 instead of pi over 4, right? And let me move this point in just a tad so it looks a little better. Say here. So this is then the vector out here from the origin. This is the vector 0, 1, pi over 2. And what about like 3 pi over 4 and et cetera, right? Well, let's just look at pi. I encourage you to plot some more points here. For the sake of time in the lecture, let me compute pi. Cosine of pi is -1. Sine of pi is 0. And then t, you just plug pi in directly. So we're even higher, right? Now we're at -1, which is backwards, kind of into the screen. -1, 0, pi. So we're like somewhere up here. -1, 0, pi. And if you trace the picture out, you get kind of a 3-dimensional spiral infinitely, which we call a helix, like a DNA strand here, or like one, DNA is intertwining 2 helix curves that are intertwined. Here's just one of the curves, right? And that's given by cosine of t, sine of t, t, the vector, right? The vector r of t equals cosine of t, sine of t. T describes a helix of kind of radius 1 here. And what's one way we can think about this? The helix in particular. If you look at the 2-dimensional vector valued function cosine of t I hat plus sine of t j hat, this is a circle of radius 1, right? And so as t goes from 0 to 2 pi, or not even, let's look at t and r like an infinite. Whoops. If t is an r, you start at 0, you go around to 2 pi, you come back once. And once you get over 2 pi, now you just start winding over and over and over this same circle, right? You're winding and winding and winding for an infinite amount of time. And as t is negative, you're winding backwards, right? Now, when you add the third dimension to this, plus tk hat, what is this telling you? This is telling you now that instead of going around in circles on this 2D plane, this says, well, as you go around, you lift. And so imagine taking a circle like winding a circle around, and then you start to lift your pencil and go like up towards positive infinity and down towards negative infinity. The picture you trace out is a helix. You're taking a circle, and then you're starting to go up towards infinity and down towards infinity. So that's how you can think about what this parameter or what this third component of a vector is doing. The first two components tell you what's being traced out in two-dimensional space, like what's being traced out in the plane, right? A circle is being traced out in the plane, right? But the third component tells you, well, at that time when you're tracing out this two-dimensional shape, you're actually at a different height. You're not just on the plane. Now you're at some different level here. And so in this case, when it's a circle, the result is a helix. And you can have a lot more interesting results than just a helix. And we'll explore that in the homework and in recitation. So now I'd like to switch gears to quickly discussing limits and continuity. So let's look at limits of vector valued functions. Okay, so let's just start with a definition. A vector valued function R of t approaches the limit L as t approaches A. And here, notice, let me write it in red, the limit of a vector valued function is a vector. The limit of a scalar function is a scalar, right? Notice now our functions are outputting vectors, so the limit is a vector. How do we denote this? Here's some notation. And it's nothing new. It's the limit as t approaches A of the vector valued function is L, right? So we take some function, some vector valued function R of t. We have the limit as t approaches A, and we see what that vector approaches, right? So what is a limit doing? We have some curve, say here's A, and here's a t value. So here, let's draw in red. This is my limit vector. Now, what does the limit look like, right? Well, it's a vector. Here's some t value. And as t approaches A, these vectors get closer and closer to approximating this vector L. And then eventually, if possible, once t is exactly at t equals A, see, we can't always have that if there's like an asymptote or something else with the function. You're getting infinitely close to this limit vector L. And sometimes you can hit it itself, and sometimes you just have to approach it infinitely close and get like infinitesimally close to this limit vector. So the idea behind the limits is the same, except now instead of just points approaching, you're looking at the behavior of a vector or a family of vectors as it approaches another vector. And so this gives us an idea for what it is, but this doesn't do us any good in terms of computing it, right? So here's a theorem that we can use to our advantage when wanting to compute limits of vector valued functions. Let's let f, g, and h be continuous functions of t, then if r of t, so let me say quickly, this is the 3D version of the theorem. 2D same without k hat. Okay, so the 2D version of this theorem is analogous. Just delete, just take the theorem kind of tunnel vision without the variable z or k hat. Okay, so if r of t is the vector valued function f of t I hat plus g of t j hat plus h of t k hat, and their limits exist. So limit as t approaches a of f of t, limit approaches t, or excuse me, limit as t approaches a of g of t, and the limit as t approaches a of h of t. If they all exist, then here's kind of the meat and potatoes of the theorem. So the limit as t approaches a of r of t equals the limit as t approaches a of, now what is this, right? What's r of t? It's f of t I hat plus g of t j hat plus h of t k hat. And here's where we'll use the this theorem to our advantage when doing computations, is the theorem states that you can pass from the limit from the outside of the vector to each component individually. So this is the same as the vector limit. Let me give myself some more room. Same as the limit as t approaches a of, whoops, of f of t I hat plus the limit as t approaches a of g of t j hat plus the limit as t approaches a h of t k hat. So this theorem, what it says is that to compute the limit of a vector valued function, you just have to compute the limit of each component, right? You look at the function of a single variable in each component, you compute their limits, and that vector is the limit vector. So here, right, what I have at the very end, I'll box it in blue. This is a vector, right, where each component of this limit vector is the limit of the respective functions, right? And so this will make it much easier to compute limits. So let's see an example. Let's find the limit as t approaches 3 of r of t, where r of t is equal to 2t minus 4 over t plus 1 I hat plus t over t squared plus 1 j hat plus 4t minus 3 k hat, okay? So let's compute the limit of this vector. The limit as t approaches 3 of r of t, well, by the previous theorem, we know that this is the same as the limit as t approaches 3 of 2t minus 4 over t plus 1 in the x component, I hat plus limit as t approaches 3, t over t squared plus 1, j hat plus limit as t approaches 3 of 4t minus 3 k hat. And notice all of these limits are very nice. You can solve it with just a simple algebraic step by plugging in the limit, because the function exists at the limit, at the end value for t, right? All three of these functions exist at t equals 3, so there's no problem. If they fail to exist at the at your ending t value, then you'll have to turn to Calc 1 and Calc 2 tricks that we learned about limits, you know, any sort of algebraic simplification to cancel the denominator, L'Hopital's rule, sine and cosine identities, stuff like this. But for now, these limits are pretty easy, so we can just plug in 3 directly. And if we do that, we'll get 2 times 3 minus 4 in the first component in the numerator, which is 6, right? Minus 4, which is 1, or excuse me, which is 2. And then we have 2 over 3 plus 1, which is 4. So we should have 1/2 I hat plus, and then let's look at j hat. Plug in 3, you get 3 over 3 squared plus 1, so that's 3/10 j hat, and then plus limit as t approaches 3 of 4t minus 3. Well, that's 12 minus 3, which is 9 k hat. So our limit vector of the function, so the limit as t approaches 3 of r of t is 1/2 3/10 9. And this is our limit vector, 9. Okay, and then so this is how you compute limits. Thanks to this theorem, you just have to compute limits component-wise to find the limit of a vector valued function. Now, I want to quickly define continuity of a vector valued function, and then we'll break, and then in the next video, we will have the necessary tools to talk about calculus of vector valued functions. So let's give a quick definition to wrap up the video. A vector valued function, r of t, is continuous at t equals a if the following 3 conditions hold. And we need all 3 of these conditions to hold. It does not suffice for 2 of the 3 or 1 of them to hold. We need all 3 of these to hold. Okay, and here's the 3 conditions for a function, or a vector valued function to be continuous. We have that r of a exists. So like where we're stopping for our t value, that must exist, like the function at that t value must exist. We also must have that the limit as t approaches a of our vector valued function r of t exists. And the third condition, which is probably the most, like when you think about continuity of a function, this is usually what you go to, but you do need 1 and 2 to also hold. That the limit as t approaches a of r of t is the same as the function at the a value. So the limit as t approaches a is the same as the function at a, okay? And a last mini definition here, or not a mini definition, but one that I'd like to include is if r of t is continuous for all t, then we say r of t is continuous everywhere, or just continuous. Sometimes we'll just say, let r of t be a continuous function. And what we mean is that it's continuous everywhere. And what we mean by that even more is that all 3 of these conditions hold for every a value, okay? And so that's where we'll wrap up in this video. And now we're well equipped to discuss the calculus of vector valued functions.